Hello, science fans. Today, let's talk about an element that you might think is just for party balloons and squeaky voices. But there is so much more to it than that. I'm talking about helium. On the periodic table of elements, it's number 2, right after hydrogen. Its symbol is He, which is pretty easy to remember. With an atomic number of 2, a helium atom has 2 protons and 2 electrons, making it super simple in its structure. It's the second most common element in the entire universe, which is pretty amazing when you think about it. It's everywhere out there in the cosmos, a true universal superstar. Now, why do we call it a noble gas? Well, it's not because it wears a tiny crown, but it's close. Helium belongs to a special group of elements on the far right side of the periodic table. These elements are known as the noble gases because they are very stable and unreactive. Think of them as the cool, calm, and collected members of the elemental family. They have a full outer shell of electrons, which means they don't feel the need to bond with other elements. Helium is perfectly happy all by itself, which is a very important property that we'll explore. This chemical standoffishness makes it incredibly useful for all sorts of scientific and industrial jobs. Let's get down to some basic facts. At room temperature, helium is a gas. You can't see it, you can't smell it, and you can't taste it. It's completely invisible to our senses. Its atomic mass is approximately 4.0026, which makes it incredibly light. In fact, it is the second lightest element that exists, with only hydrogen being lighter. This feather-light quality is the secret behind its most famous trick making things float. But its lightness is just one piece of a much larger and more fascinating puzzle that we are about to put together. Consider this. Everything we know about helium starts with these fundamental, simple properties. So, we have this colorless, odorless gas that doesn't like to react with anything. That might sound a little boring, but its refusal to interact is exactly what makes it so special and safe for certain applications. For instance, this non-reactivity is a huge advantage over its lighter cousin, hydrogen. While hydrogen is also great at lifting things, it's extremely flammable. Remember the Hindenburg? That's why we prefer the noble, stable, and much safer helium for our party balloons and parade floats. It provides all the lift without any of the explosive drama. It's science in action, keeping our celebrations safe.
Believe it or not, we discovered helium somewhere truly out of this world. We found it on the sun. Back in 1868, a French astronomer named Pierre Janssen was observing a total solar eclipse in India. He used a special instrument called a spectroscope to study the light coming from the sun's outer atmosphere. He noticed a bright yellow line in the spectrum that didn't match any element known on Earth at the time. He thought he had found something completely new, a substance that existed only on the sun. It was an extraordinary moment in the history of science, finding an element 93 million miles away. Around the same time, an English astronomer named Norman Lockyer also observed this mysterious yellow line. He was the one who concluded it must be a new element. He proposed the name helium, which comes from the Greek word for the sun, helios. How cool is that? An element named after the star where it was first seen. For about 30 years, scientists believed helium was exclusive to the sun and other stars. It was a celestial element, a piece of the cosmos that we couldn't find here on our own planet. This solar origin story makes helium unique among the elements. Then, the story took a turn and came back down to Earth. In 1895, a Scottish chemist named Sir William Ramsay was conducting experiments with a mineral called cleveite. When he treated the mineral with acid, it released a gas. Curious, Ramsay collected the gas and analysed its spectrum. To his astonishment, he found the exact same bright yellow line that Janssen and Lockyer had seen in the sun's light decades earlier. Helium wasn't just in the stars, it was right here, trapped inside rocks on Earth. This was a monumental discovery that connected our planet directly to the chemistry of the sun. So, how did helium get trapped in rocks? It's a product of natural radioactive decay. Heavy elements deep within the Earth's crust, like uranium and thorium, slowly break down over millions and millions of years. As they decay, they release tiny particles, which are actually helium nuclei. These particles get trapped in pockets of natural gas underground, where we find and extract them today. So the helium in your balloon might have been created eons ago, deep beneath your feet. It's a little piece of ancient Earth history, floating on a string. Consider that. Let's get back to that floating balloon. Why does it float? It's all about density. Density is how much stuff is packed into a certain amount of space. Helium is much, much less dense than the air around us. The air we breathe is mostly a mix of nitrogen and oxygen, which are heavier than helium atoms. So, when you fill a balloon with helium, it's like a bubble of superlight gas in a sea of heavier gas. The surrounding, denser air pushes up on the balloon with more force than the balloon's weight pushes down, causing it to rise. It's the same principle that makes a log float in water. It's buoyancy in action. Now, let's talk about safety. As we touched on, hydrogen is even lighter than helium and would make balloons float even better. But hydrogen has a big problem. It's highly flammable. A single spark can cause hydrogen to react explosively with the oxygen in the air. Helium, being a noble gas, is completely inert. That means it won't burn or react with other chemicals. This makes it the perfect, safe choice for everything from children's birthday parties to the giant floats in the Macy's Thanksgiving Day Parade. Safety is a key part of good science, and using helium is a prime example of choosing the right element for the job. But helium's superpowers go way beyond floating. It plays a critical role in modern medicine. Have you ever heard of an MRI machine? MRI stands for magnetic resonance imaging. These incredible machines let doctors see inside our bodies without any surgery. To work, they use extremely powerful magnets, and to get that power, the magnets need to be kept incredibly cold. That's where liquid helium comes in. Helium becomes a liquid at an astonishingly low temperature, minus 452 degrees Fahrenheit, or minus 269 degrees Celsius. It's one of the coldest substances we can work with, making it the ultimate coolant for MRI magnets. Helium also helps people breathe. For patients with severe respiratory issues like asthma or COPD, breathing can be a real struggle. The air can feel thick and heavy, making it hard to get enough oxygen into the lungs. Doctors can give these patients a special breathing mixture of oxygen and helium called Heliox. Because helium is so much less dense than nitrogen, the main component of air, the Heliox mixture flows much more easily into the lungs. This reduces the effort of breathing and helps deliver oxygen more efficiently. It's a simple idea from physics that has a life-saving impact. Helium's extreme coldness isn't just for MRIs. Scientists who study quantum mechanics and superconductivity rely on liquid helium to create the ultra-low temperatures needed for their experiments. At temperatures near absolute zero, matter starts to behave in, well, very strange and wonderful ways. Liquid helium itself becomes a superfluid, a state of matter that can flow without any friction at all. It can even climb up the walls of its container and flow through microscopic cracks. By using liquid helium as a coolant, researchers can unlock the secrets of the universe at its coldest and most fundamental level. Science is cool, and liquid helium makes it even cooler. In the world of industry, helium is a silent but essential partner. In high-tech welding, especially for materials like aluminum and titanium, it's important to protect the hot metal from reacting with the oxygen and nitrogen in the air. If they react, the weld becomes weak and brittle. Welders use helium as a shielding gas. They blow a steady stream of inert helium over the weld area. Because helium doesn't react with anything, it creates a protective bubble, allowing the welder to create a pure, strong, and clean bond. It's kind of like an invisible shield that makes our cars, airplanes, and structures safer and more durable. Let's dive deep, literally. For professional divers working at great depths, breathing normal compressed air is dangerous. The high pressure can cause the nitrogen in the air to dissolve into the bloodstream, leading to a condition called nitrogen narcosis, which impairs judgment. To avoid this, deep-sea divers often breathe a mixture of helium and oxygen. This trimix or heliox is safer because helium doesn't have the same narcotic effect as nitrogen under pressure. It allows divers to work deeper and for longer periods, exploring the ocean floor or performing complex underwater construction and repair tasks safely. From the depths of the ocean, let's blast off into space. Rockets that use liquid hydrogen and liquid oxygen as fuel need a way to keep their systems running smoothly. As the fuel tanks empty, something has to fill that space to keep the tanks pressurized and structurally sound. You can't just leave a vacuum. The solution? Helium! Super cold helium gas is pumped into the fuel tanks to force the fuel into the engines and maintain pressure. It's light, it's inert, and it stays a gas even at the cryogenic temperatures of the liquid fuel. From lasers to rockets, helium is the unsung hero of some of our most advanced technologies. Did you know there are two main types of helium atoms? They are called isotopes. The most common one is helium-4, or He4, which has 2 protons and 2 neutrons. This is the helium we've been talking about, the one that comes from radioactive decay inside the Earth. Then there's its rare sibling, helium-3, or He3, which has 2 protons but only 1 neutron. He3 is extremely rare on Earth, but is believed to be more abundant on the Moon. It's a potential fuel source for future nuclear fusion reactors, a clean and powerful way to generate energy. So helium isn't just one thing, it has a family with some very exciting potential. Now for a serious topic, helium is a finite resource. This might sound strange since it's the second most abundant element in the universe. But here on Earth, it's a different story. Because helium is so light, any that escapes into the atmosphere doesn't stick around. It just floats up until it's lost to space forever. Unlike other resources, we can't make more of it. The helium we have is what has been trapped underground for billions of years. We get it as a byproduct of natural gas drilling, and once we use it and it escapes, it's gone for good. This brings us to some common myths. A big one is that helium is endless. As we just saw, that's not true for us on Earth. We are using it up much faster than it's being produced naturally. Another myth is that breathing a little helium to make your voice squeaky is completely harmless. While a small amount is usually fine, inhaling helium directly from a pressurized tank is extremely dangerous. It can displace the oxygen in your lungs, leading to dizziness, fainting, or even suffocation. It's not a toy, and it's certainly not something to be careless with. Safety first, always. So, what does this all mean? It means we need to be smart about how we use helium. It's essential for so much more than balloons. It's vital for medical imaging, for scientific research, and for our space program. We need to prioritize these critical uses and find ways to recycle and conserve every bit we can. Helium is a truly remarkable element, a gift from the stars and the Earth itself. By understanding its importance and its limits, we can ensure that its amazing properties will be available for the innovations and discoveries of tomorrow. Let's protect this noble element.